Welcome to Mrs. Z's Chemistry. In this video, we will begin our study on gases and liquids. We will start with learning about the kinetic molecular theory. If you remember back from chapter 1, we learned that a scientific theory is not just an idea or a speculation or a hunch or a guess. It is in fact an explanation of the scientific facts that we've recorded, collected, observed, and experimented with. So, according to kinetic molecular theory, a gas consists of a collection of small particles that are in continuous random motion. And these small particles, these individual molecules, we say do not occupy a volume. Or you can say that the volume is so small it is negligible. So when we talk about a volume of a gas, we are discussing the volume of the whole collection. In other words, the volume of the container that is containing the gas. The collisions between molecules are perfectly elastic. That means that there's no energy or that is gained or lost during the collision. There are also no attractive forces or repulsive forces between the molecules. Later on in this chapter, we will learn about liquids and how let's just say a water molecule, here's our oxygen, and then the two hydrogens are usually located in a bent shape on the molecule. We know that we've got covalent bonds between the oxygen and the hydrogens, and the oxygen and the other hydrogen. And those are the covalent bonds that we've been talking about from chapter 7. The forces that are holding the molecules together in a liquid would be something called an intermolecular force, and it's an attraction between the two molecules. And we will talk more about that in 9.5. In gases, the molecules are so far apart that there are no attractive or repulsive forces felt between the molecules. And the last point that we're going to discuss in kinetic molecular theory is that the average kinetic energy of a molecule is directly proportional to the temperature of the whole system in Kelvin. So in these equations and problems that we are going to be solving, we must have our temperature in Kelvin, not Celsius or Fahrenheit. Speaking of the equations, we have a variety of different variables that we can use to describe the gas. We have pressure, volume, temperature, and moles. Let's look at pressure a little bit more. Pressure is the result of the collisions between the particles themselves and then also between the particles and the walls of the container. If there are more collisions happening within our container, then that means the system has a higher pressure. If there are a lower amount of collisions, then that is a lower amount of pressure. These are some pressure units and conversions. We have ATM, which is atmospheric pressure. Room pressure is said to be 1 ATM. If you imagine all of the air molecules floating around in the room, the amount that are colliding with our body is felt as 1 atmospheric pressure. 1 atmospheric pressure is equal to 1.01 times 10 to the 5 pascals, or 101.3 kilopascals. 1 ATM is equal to 760 millimeters of mercury, and 1 ATM is also equal to 760 torr. ATM, millimeters of mercury, torr, and pascals are all just different units to describe pressure. Now let's go ahead and discuss Boyle's law and how all of these different variables, volume, pressure, temperature, and moles, are related to each other. Boyle's law says that when the quantity of gas is unchanging, as well as the temperature is unchanging, then the volume is inversely proportional to the pressure. So let's take this first picture here. Imagine we have some container at a certain volume and a certain pressure. The temperature is going to remain constant, and if we were to decrease the volume, then the pressure must increase. You can imagine if there's a smaller space for the particles to be moving around, more collisions are going to be happening at a higher rate. So that increases the pressure. Pressure increases when volume is decreased, and pressure decreases when volume is increased. And these are going to increase and decrease by the same factor. So if the volume decreases by half, then the pressure will double. Or if the volume increases by a factor of 5, then the pressure will decrease by a factor of 5. So looking at this sample problem that says the volume of some amount of gas was 1 liter when the pressure was 10 atm, what would the volume be if the pressure decreases down to 1? So look at the pressure and realize that the pressure has decreased by a factor of 10, from 10 atm to 1 atm. That means the volume needs to increase by a factor of 10. So the volume, would starting out at 1 liter, would increase to 10. Now let's look at Charles' law. When the quantity of gas is constant, as well as the pressure is constant, then the volume is directly proportional to its temperature. So as volume increases, temperature must also increase by the same factor. Looking at this first picture, we have some volume. You can imagine that there's a certain level of pressure because of those molecules that are colliding with each other in the walls of the container. If we were to increase the volume, say double it, you would automatically assume, based on Boyle's law, that the pressure should decrease. However, if we want to keep pressure constant, then our temperature must increase. Raising the temperature increases the speed or velocity of the molecules. Therefore, we will have the same amount of collisions, keeping the pressure constant. As volume decreases, temperature will also decrease in order to keep pressure constant. A gas occupies a volume of 6 liters at 25 Kelvin. What would its volume be at 100 Kelvin? Well, looking at the temperature, we can see that the temperature has increased by a factor of 4, from 25 to 100. Therefore, the volume needs to also increase by a factor of 4. It started out at 6 liters times 4 equals 24 liters is the final volume here in this sample question. Now let's look at Avogadro's law. When we have constant temperature and pressure in our system, then the volume of gas is directly proportional to the number of moles of the gas. So looking at this first picture, you can imagine we have a certain volume, and because of the certain number of particles that are in that container, we have a certain pressure and temperature as well. Now, if we were to double that volume, but we want to keep the pressure and temperature constant, we need to also double the amount of moles that we have, double the amount of particles that we have in our container in order to keep pressure and temperature constant. So volume is going to increase as the number of moles increase, and the volume will also decrease as the number of moles decreases. These are these equations that come from the relationships that we've just discussed. Boyle's law says that the initial pressure times the initial volume multiplied together will equal the final pressure times the final volume. Charles' law has V1 over T1 is equal to V2 over T2. The ones meaning the initial or beginning values, and the twos the ending or the final or the new values. And then Avogadro's number says that V1 over N1 is equal to V2 over N2. We use N as a variable for moles to mean the number of moles. And this is because M is often used in many other equations, as well as the abbreviation for meters. So to not get it confused, we're going to use the variable N for moles. Now, if we were to combine Boyle's law and Charles' law, and we're going to keep the number of moles of gas in the system constant, then we can have these two different equations combined into one equation called the combined law. P1 times V1 divided by T1 is equal to P2 V2 divided by T2. Before we do any of the sample problems, let's look at temperature again. You must always use temperature in Kelvin. Because we said that the relationships are going to be inversely or directly proportional, if the Kelvin temperature were to double, we need the volume to either double or decrease. All the other variables are going to increase or decrease by that same factor. Doubling Kelvin doesn't necessarily mean the same temperatures in Celsius have doubled either. So that's why we must convert our temperatures into Kelvin. Here's the first sample problem. 1 liter balloon at 25 degrees Celsius has a pressure of 750 millimeters of mercury. If the temperature is increased to 37 degrees Celsius and the pressure is decreased to 740 millimeters of mercury, what is the new volume? Our equation should be the combined equation, the combined law, because two of our variables are changing. So if we take P1 over V1, or P1 times V1, and here's our combined law. We are going to be solving for V2 because it says what is the new volume? That's the second volume, and we're given all of the rest of the variables. So using algebra, we are going to rearrange this. We're going to multiply both sides by T2, and we're going to divide both sides of the equation by P2, and this isolates V2 on one side of the equation. When we plug in all of our values, we get an answer of 1.05 liters. See if you can pause and work this problem out before seeing the answer. We're going to use Charles' law here, which says V1 over T1 is equal to V2 over T2, and that's because even though we were given a value for pressure, 750 torr, that's the pressure unit, the pressure did not change, so pressure was constant. So we can just leave out the variable of pressure, and we're left with just volume and temperature changing. Plug in our values, and we get 0.321 liters. Pause and work this problem out. This problem is easiest to solve by using cross multiplication. The cubic centimeters here is the unit for volume that we're using, and we do not need to convert it to liters. Volume and pressure can stay in whatever unit is given in the problem, only temperature must be converted to Kelvin. Solve and work this problem out. We need to use Boyle's law here. PSI means pounds per square inch, and that was a pressure unit, as it told us in the problem. However, you didn't need to know any of the conversions or how it relates to atmospheric pressures or torr, millimeters of mercury. It doesn't matter because your PSI ended up canceling. And again, you don't need to convert your volume to liters. You can leave the volume in milliliters. This answer is rounded to two significant figures. See if you can solve this problem. Almost identical to problem 4, where we use Boyle's law. Our PSI is canceling, and we're left with milliliters. See if you can pause to work this problem out. In this problem, we're going to use Avogadro's number, and we can solve through cross multiplication. We find that N2, or the final amount of moles, is 8.2 moles. However, the tricky part in this problem is that the problem is asking for how much neon gas was added. So we didn't add 8.2 moles, we ended up with 8.2 moles, and we had started out with 3 moles. Therefore, if you subtract, you can find out that 5.2 moles of gas is what was added to the sample. See if you can solve this problem. Charles' law. This one can also be solved with cross multiplication. And our last example here, problem 8, see if you can pause and solve this problem. The tricky part of this problem is that the problem is telling us that if 5.61 moles of methane gas was added, there's the key word. So 5.61 is not N2. N2, or the final amount of moles, is the initial value of moles plus what was added, the 5.61. So our N2 is actually 7.75, which goes here in the equation. When we cancel our mole values, or our mole units, then we're left with 21.7 liters.